Hello, ladies and gentlemen. Thanks for tuning in again today to GGS300, so Quantitative Methods for Geographical Analysis. In reality, this is the first lecture of the term. So the previous video that hopefully you've all watched now is really just covering the course policies and the syllabus outline, whereas today I'm actually going to start to get into some of the content for the materials that we're going to cover this term. So within this presentation today, I'm going to cover a little bit around why we use quantitative methods. I'm going to talk a little bit about history. I'll start at history and then I'll get into some scientific philosophy, and then we'll actually get into some definitional issues and just run over some basic concepts for how we conceptualize and structure data in the second part of this lecture today. And that's really going to be kind of laying a platform in order for us to actually build on in the future lab work, particularly for when we start to actually pick up our studio and use that to actually do data analysis. So before we begin, I just kind of want to go back to the very beginning, talk a little bit about why we use Quant, how it developed, and really there's a little bit of history here. So when did numbers and the alphabet first start to emerge? Well, actually, if you go back about 3,000 years, that's when the alphabet and numerals started to first be kind of formalized. And that was generally because people needed to trade. So actually, if you go back, it was the Phoenicians who had one of the very first alphabets. So that's modern day Lebanon, Israel, Palestine. And actually, if you go back, then basically they were trading all over parts of the Mediterranean, ancient Greece, ancient Italy, North African coastline, all the way along here. And if you're going to be trading goods and you need to be able to keep track of goods that you need to send and money that you receive, then you basically need an accounting system. And that's essentially why we ended up having numerals being created in order to apply these to problems that people needed to solve at this time. And that was kind of the scaling up of trade. You can't necessarily go back and say that math was developed at one specific point. There are, in reality, important contributions that were actually provided by a variety of different civilizations. So, for example, the Egyptians, the Greeks, the Romans, the Chinese, the Persians, as well as many others, all made important incremental developments for what we now essentially start to see as math. At least this is in the ancient period. Then when we kind of fast forward to particularly the last 500 years, we had the beginning of the Enlightenment, some of the philosophical concepts for the Enlightenment actually taking root in about the 17th century. So here I'm just covering Francis Bacon, who's widely regarded as being the father of empiricism. So if you think back then, essentially you had religion as kind of the main way for people to kind of perceive the world, and it was really much more of a belief system, religion, as opposed to the concept that Bacon put forward, Francis Bacon, which was a philosophical concept, which is empiricism. And essentially empiricism is actually understanding the world through observation, so gaining facts through actually observing the world around us. And this is very much still the standard way now that we approach science is, in many cases, at least empirical science, through observation. So we theorize about how the world works, and then essentially we go out and try and get data to see whether that theory is correct or not, and then we make a decision about that potential theory, and then we might go back and repeat that process. So Francis Bacon is an important figure in this because it really kind of laid the groundwork for the scientific revolution that really kind of kicked off around the 18th century, okay? So actually, if we go back to this really kind of pivotal time, this was when there were some major changes happening in the world. So particularly Newton's theories that were developed, which were kind of the basis for science. So in his publication of his Philosophy Naturalis Principia Mathematica, which contained some of those the mathematical approaches for things like theorizing and modeling gravity, for example. And this was really revolutionary before, given the fact that religion was kind of the main prevalent way to see the world, and actually Newton was able to work out that there were these general principles that could be identified and mathematically represented, such as the force on an object is related to the size of the object and its distance. And that was really pivotal at that time. And there were so many other important events that happened around this period that eventually led to the Enlightenment. So that was the shift away from the divine right of the monarch. So that was particularly relating to the American Revolution, the French Revolution, and this was a major start for how the scientific revolution essentially started out. What's really interesting about Newton's gravity models is that they actually hold up not just for physical systems like the planets, but also for socio-economic processes as well. So if you actually look at the trade flows between cities, it turns out that a gravity model is actually pretty good at describing the size of the potential trade activities between different cities based on their sizes and their distances. And this has kind of been a bedrock application, this type of model, for the last 40 or 50 years in global trade and in kind of regions analysis as well. So it's been applied many times over. And some of you may know of Paul Krugman, so a Nobel Prize winning economist, and actually his international trade model is heavily based on these types of gravity models that take inspiration from Newton's original models. So the science that's around this really has had such a pivotal impact on society. I mean, it underpinned how a man was landed on the moon, and that math is still relevant today, essentially. And actually the impact that both of these characters have had on society and the development of the US, in fact. And here's just one example of how big that impact has been. So this is actually the Library of Congress, so it's just behind the Capitol. If you haven't been, I'd thoroughly recommend that you go. I mean, I really love the building. I think it's one of the most beautiful buildings easily in North America, but also across the world. So if you go in, actually I think it's shut at the moment due to COVID, but if you go in and you go to the viewing gallery where this photograph is taken, you can actually see Francis Bacon is in the very centre here. He's one of the 12 statues, so he's in there as one of the people representing philosophy, for which there are 2 statues. I think Plato is the other one. And then so Isaac Newton is actually also in the statues just here. I think it's just to the left out of the picture view. But if you get an opportunity to go, I thoroughly recommend that you go and take a look, because it's such a beautiful building. You can just see how much marble is involved in some of the architecture here. So, okay, well, that's a little bit about history. Now let's get into some of the definitions. Okay, so what do we really mean when we say quantitative? All right, what does that actually mean? So maybe take a minute to pause, think about what that actually means. I've just decided to put here, the Oxford English Dictionary definition for that. So that's essentially relating to some sort of measure or quantity. So that's the fact that some aspect of some entity essentially can be measured in some sort of number, amount, size, or weight. And essentially coming from the Latin for quantitas. So why do we measure? Why would we do this? Well, there's multiple different ways, multiple different reasons for why we want to measure things. I think firstly, something that we all do on a daily basis, it provides us with a consistent method to actually standardize. So if we're baking a cake or if we're paying our electricity bill, then we're going to need to have a quantitative measure for the number of ingredients that we're going to add, the proportions, or we're going to need to know how much energy we've consumed in order to pay that bill. So that's kind of a more mundane reason for why we want to measure things. It's useful for management, for making decisions, for trade. But then on the second point just here, I'm just also emphasizing the fact that the beauty of having quantitative methods is that it allows us in a very scientific way to actually delineate why differences occur between different entities. And therefore it really underpins how we ask questions about the world, how the world works in essence. And this is obviously essential because we want to be able to understand it, and you can't really robustly say anything about the world unless you're actually able to measure it in quite a reasonably precise way and actually be confident in the conclusions that you draw. And a key part of this actual course, as I will get to in the next few weeks, is that we're able to do this in a quantitative way and explain how we're able to reach conclusions or perhaps but how we're able to accept a hypothesis or reject a hypothesis and therefore reach a conclusion based on the ability to actually measure different relationships that are taking place. So natural science is quantitative. So that's the physics, the chemistry, the Earth systems, a lot of the things that are going on in the GGS faculty. This is us trying to understand systematically how things work, and we're interested in trying to understand the general patterns. So imagine there's lots of noise in a process that we want to understand. We're trying to understand what the key ingredients are that's actually driving that process. And we want to be able to develop predictive models from that insight that we actually gain, okay? So this is kind of the key backbone for what we're actually trying to do in natural sciences. In the social sciences, they are still actually heavily quantitative. So actually, just as one example here, even within sociology, which has a lot of qualitative researchers, they actually estimate that approximately 2/3 of those papers that have been published for about 80-year period, 70-year period, were actually quantitative. So, even in the social sciences, which has more of a leaning at times towards some qualitative methods, still heavily using quantitative methods because it's, the bedrock for how we actually understand the world and how we're able to draw conclusions which we can essentially put some sort of precision on the level of reliance that we can have in those. So this is incredibly tribal, and I'm not going to get into it too much, but the debate versus the quants, the quantitative people, and the qualitative researchers is really quite heated. And I actually had to cover some of this content when I was studying for my master's degree, and it gets really quite heated. So I'm not going to get into it too much here. I just want you to be aware that there's some quite strong beliefs around this. So the quants are very much set in their ways about how you actually do science, how you draw conclusions about the world in a robust way, and I would arguably put myself more in that camp these days than the qualitative camp, whereas the qualitative researchers will make a range of at times quite justified claims about the limits of quantitative research, and I think they both play a very important role in being able to understand all of the different things that we're interested in. So maybe quant's very good for some pure science topics, but then particularly when you're studying social systems, because you have behavioral change, there are definitely times where qualitative data and qualitative insights can provide you with a kind of a more rich insight into why things happen. So as I've kind of explained very briefly, quant's often kind of criticized for being reductionist. So we're going to reduce a process which maybe has 20 different factors influencing its outcome down to 3 or 4 factors which explain the majority of the variance in the data. So let's say 3 or 4 factors explain 60% of the data. Well, I'm just going to use those 3 or 4 factors to build my predictive model. I don't care about the fact that 40% of the data can be explained by another, so let's just say 16 factors. That's just way too much complexity for me. What we're trying to do here is just get the simplest model, the most elegant solution, with the least number of explanatory variables in order for us to generally understand the process that's happening, whether that's explaining house prices in Fairfax, or whether that's trying to understand the COVID implications on the labour market. So this is kind of the driving point of quantitative research. I think the issue starts to come with qualitative research. So for example, if I sent you out and I said I want you to go out and survey a bunch of people, or maybe just actually interview, maybe I want you to go out and interview students on their perceptions of learning at GMU during the middle of a global pandemic, okay? And you're going to come back to me and you're going to give me, let's say you managed to do 50 interviews, which is actually quite a lot. It's quite hard to generalize those 50 interviews because there'll be a lot of nuanced data in there. It's very rich. That's a good aspect of qualitative research. But actually, it's quite hard to externally generalize those opinions because you don't know necessarily if the opinions that you've been given through those surveys are really representative of everyone at the whole university. So this is one of the kind of limitations of qualitative research. It gives you a really rich amount of data, but then it's quite hard to kind of generalize beyond the sample that you've collected to the wider population. And if you don't understand some of those terms that I just used there, the sample, the population, well, I'm going to go into that just very shortly. So hopefully it will be clear to you by the end of this lecture. So there's a whole load of different methods that you can use in order to understand the world in a quantitative way or the world in a qualitative way. There's reading which you need to do in McGrew, so the book that is affiliated with this course, you need to do that reading this week. But you know, in the book it discusses these issues. I just wanted to emphasize that there are a variety of different methods, for example. So on the quantitative side, we're going to actually be covering a lot of these methods in this course this term, which is very exciting. So descriptive statistics we'll be doing in the next couple of weeks. T-tests we will be covering in the second third of the course. So remember I said that we we're going to be focusing on difference tests. And then in the third part of the course, we're going to be focusing on relationships. So correlations, as they're described here, regression analysis we will be getting into. So how do we understand the relationships when there's lots of different factors involved? And although we're not covering it in this term, I just wanted to point as well to predictive methods, because I think some of you will all have been hearing a lot of noise and hype around machine learning right now. There's a lot of excitement across the academic world and industrial world around these sets of techniques. And they're really not that different from what you're learning in this class. So we're going to be learning some basic probability. We're going to be learning some models which are very similar to the underlying workings of these machine learning predictive models. So I just wanted to point to that for the future, if you're interested in that kind of world, this really is kind of a basic course that you need to take in order to progress to that level. So that's the quant side. On the qualitative side, you have all sorts of different techniques ranging from observation and ethnography through to interviews. Maybe you go and you actually speak to people, you record their responses to the dialogue that you have, and then you analyze that. Focus groups, so that's maybe where you get 6 or 7 people together and you ask them a set of questions, and they work as a kind of ask questions to the group, and there's discussion between those people, and then you record that data. Surveys, so this can be done in a very comprehensive way. Actually, if you design this correctly, you are able to externally generalize those surveys back to the rest of the population. So that's quite a nice technique. Actually, a lot of the statistics that you might get from the National Statistics Bureau, so the Bureau of Economic Statistics, that lots of countries have, or if you want to get census data, a lot of that will be based on survey-based approaches. So they're actually quite robust if you know how to design them properly and you've got the resources to undertake them. And then there's also document analysis. So that's just a bit of a background about the history of quantitative analysis and basic definitions around the kind of tensions between quantitative and qualitative approaches. And obviously in this course we're focusing on the quant side. That's not to say that one is better than the other. What I would say is that if you're interested in qualitative, you can still apply the quantitative techniques to those qualitative approaches. Actually, there's quite a sophisticated set of techniques that can be applied there now. So, for example, if you have a cell phone and you're using Siri, or you're using some sort of voice recognition, that's essentially natural language processing, and that's the computer in your phone is running some code, and they're trying to estimate what the answer should be to a set of questions, a question that you've given to Siri, for example. So this is just an example of how actually the qualitative and the quantitative worlds are beginning to merge, and there's some really cool techniques that are potentially available in that area, but it's beyond this course. Okay, so within this I want to go over some basic statistical definitions. And there's 2 different types of statistics, and I've kind of already mentioned them a bit, and actually I think if you started to read in the book, you'll kind of pick up that there's different flavors. So on the descriptive side, we have these kind of often single metric numbers which represent a set of data and kind of represents some of the underlying patterns within that data. On the inferential side, what we have are more sophisticated ways to identify differences between different groups of sample data, for example, or ways to identify relationships within the data. So think of this as kind of descriptive is a very important part of understanding your data. When you get a data set, you need to run these descriptive stats. These are generally easier to understand Then the inferential part, that's probably where you're going to go in the end, but it's more complex and you need to have a good understanding of what's happening in the data first before you get to that point. So that's why these are kind of mutually beneficial. So I have put in definitions here for those two different types. So I actually put the definition for descriptive stats as essentially quantitatively summarizing the main dimensions of, in this case, let's just say it's spatial data, using a set of standard metrics. And there's, let's just say there's approximately 5 to 10 metrics which people will always use when they're doing descriptive stats. So it's the mean, it's the range, so that's that. The mean is the average, the range is the difference between the minimum value and the maximum value. Let's say we're interested in the interquartile range, so the difference between the bottom quarter and the top quarter point, or the standard deviation, so that's the average deviation around the mean that takes place. And we will get to these in the next couple of weeks, so hopefully you'll be able to start to get a handle for what some of these descriptive statistics actually mean if you're not familiar with them already. And then on the more kind of complex, more advanced side, we have inferential statistics, and I've defined it here as actually enabling you to draw inferences, so potential explanations about how the world works, about a particular population that you're going to be studying. Okay, so you're able to kind of extrapolate findings from potentially small samples to a whole population. Okay, so this is kind of the basis for some of those techniques that we will be covering in the second, third, and the final third of the course. Data definitions. Okay, so what's a variable? So essentially what I wanted to do is to think about this in terms of spreadsheets. If you're not familiar with R yet, that's fine, we will get to that. I assume most of you have used a spreadsheet, so you're used to seeing a column in a spreadsheet and a set of rows in a spreadsheet. And I'm going to basically use an example that's quite similar to a spreadsheet. Okay, so let's just assume that we've got 4 columns, and then let's assume that we have some data that we've collected about different people. So let's assume that I am ID1. In fact, I think I am ID1 because I think I'm 78 kilograms, I've got blue eyes, and I'm about 174 centimeters high. So these are my kind of characteristics. If we went round everyone in the class, we could build up a portfolio, a data set essentially of everyone's characteristics. Obviously, we don't like to record people's exact identifiable information, so we'll use an anonymous identifier, an ID, and that will represent each of the individual participants that we have in this class. And therefore, we're able to kind of develop this. Let's just say it's in a spreadsheet for now. And what we're going to do is we're going to try to understand some of those key definitions about this data set. Okay, so I asked in the previous question, before I got to this example, what's a variable? And here I'm defining it basically as an attribute of an observation that can be measured, classified, counted. And I want you to think of it in this particular instance as a column. So it's nice and easy to kind of understand that. So within this data set, we have a bunch of people, and they have different characteristics, such as eye color or height. Okay. What then is a value? So if you think a value is actually part of a column potentially, really what it is it's a single piece of numerical information in this case. So arguably it doesn't just have to be numerical, but let's just say for the sake it is here, okay? And actually traditionally a single value is called a datum. So data is actually plural for lots of individual datums. Lots of individual data values, which is made up of they're individual datums essentially. And the only reason I'm telling you that definition is because within the scientific field, if you write a paper, people might pick up on your use of data for plural or singular, so it's just important to be aware of it. Okay, but my point here is that each one of these values in these cells is obviously a value. So I've labeled it. So we've got the Z variable here, Z variable, And essentially I've labeled the values as Z1, Z2, Z3, as we go down each one of the individual participants within our sample. So what's an observation? Well, that's easy. An observation is just a single entity that we've studied, okay? So from a larger group. So just think of this as a row in a spreadsheet. And within that framework, which I have already sketched out for you, just think of this as an individual person like myself. So I'm in there at row 1. I have a specific weight, a specific eye color, specific height, and the observation is all of my characteristics as a person running across the spreadsheet, okay? So the definition of data. So it's really any numerical or non-numerical information that's available. And this is very generic and broad here, okay? So let's just say that all of this is data. What actually is a data set then? Well, essentially this, in more general terms, is it's a group of those variables that we have, often presented in a tabular format. So you can think of this as a spreadsheet, but the reality is that we're going to call these data frames when we get into R. So this is a data set. It's a two-dimensional data set, and if you've used MATLAB previously, then you'll call this a matrix. Or if you've done some matrix algebra or some other type of math, you might have come across matrices already. Okay, but so there's a different group of names that we can kind of call these aspects, but I think it's important just to kind of sketch them out and describe them, particularly to kind of pick up on what a data frame is, an observation is, a variable, because these are kind of these will be key building blocks for when we get to RStudio and we start to actually manipulate some of the data, okay? And then you should be able to think, okay, this is a particular data value, or it's a data variable, and then you kind of know what we're going to be doing in the code when I refer to those specific data types. Okay, so that's an example of maybe some data that we've collected in a spreadsheet. Now let's think a little bit about how we do some basic sampling and what we're going to be considering as a wider population, for example. So the definition of a population when we talk about this is the total set of data that are going to be studied. So I think population, you probably think about this in terms of a country. So let's just say that we're going to consider the population of Fairfax. We're going to draw a boundary around, let's say, the city of Fairfax, and everyone that lives in that city boundary is the population, okay? So it's basically everyone who lives within that one area, and there's a wide variety of people within that area. So that's going to be people of different genders, people of different household compositions, different ages, different sexual preferences. This is going to be, quite heterogeneous, quite diverse in terms of all the different characteristics that people are going to have. What we might want to do there is to actually take a sample. So let's say that we can't go out because we don't have enough time and actually survey or speak to each one of the people within the population, because it's just too many people. We don't have the resources to do that. So let's pick a subset of observations from the population, okay? So what we're going to do here is we're just going to either randomly sample or design a sample collection method that allows us to actually go and use our limited resources to just get a small selection of people that we think then we might be able to generalize to a larger area, okay? So when I say estimation here, it's really kind of getting to that last point that I just made, that this is the process of finding an approximated value. So let's say that we want to undertake an estimate for the age of people living in Fairfax. Let's assume that we don't have any other information about the people living there. We don't have the resources to carry out a full census of everyone living in Fairfax. So therefore, what we're going to do is we're going to carry out sampling approaches, and we're going to try to estimate the age overall by doing these different samples, okay? and the samples may have different numbers of people, they may have different compositions in terms of the different characteristics that the people have. And these are all things that you basically need to be aware of when you start to use these types of methods and you need to design a sample that's broadly representative of the population that you want to survey. So I'm not going to get too much more into this, but this kind of is laying the groundwork for how we actually get into designing and carrying out those sampling processes. And we will do a whole week on sampling. I mean, there could be a whole course on sampling actually, but in this case, it's just relatively minor components of the overall module. Okay, just before we get to data visualization, I realized I actually missed out one important thing, and that's that the population is actually always represented by the capital letter N. So you'll see here that's referred to the population. And then the sample is actually also referred to as N, but it's a lowercase n. So I just wanted to identify that because you will see this within the course, you will see it within the math that we carry out, and you might even see it in one of the tests. And it's important just to know the difference here because that's kind of basic statistical information. Great, let's get on to data visualization now. So before we finish this week, I just need to introduce you to some of those basic data visualization techniques. So I think in the book it starts to get into some very basic plotting. What I've basically done here is I've gone through a bunch of my past publications and I've pulled out examples of where I've used different data visualizations for you. I think that this is more constructive because then you can kind of see how a logic chain has been created. Okay, I need to go out and study this, and then in the end, once you've got the data, this is how you visualize the results. Okay, so I think that that's one reason why I've done it in this way, because it kind of gives you a concrete way to understand why something was done in a particular way. I don't want to do too much theory, okay? I want you to be able to see real applications for what we're doing. I know that myself, I don't like to learn too much abstract work. I like to really see the kind of applications, and actually things start to click a lot more for me when I'm able to see why we're learning some math. You know, if you just learn it and it's dry and it's quite hard to understand it in the very kind of abstract, raw form, theoretical form, actually when you then apply it to predicting traffic counts or predicting the outcomes of sports games or trying to predict your behavior based on your certain characteristics, I mean, that's just so interesting. So I think that by kind of pitching it in those terms, I think it should be easier for you to understand as well. Okay, so visualization is an essential tool that we have within our toolbox in order to do a range of things. So it could be to test statements about the world. It could just be to kind of demonstrate relationships that exist within the data without going towards any further quantitative methods. Oh, that's right, and I did mention Hadley Wickham's book, and I think I actually got it out of this one here. So Hadley Wickham essentially is, he's a bit of a god in the RStudio world, and you will encounter him many times on the internet, I think. So this book here, R for Data Science, is what I'm actually quoting here. You don't need to buy this, but actually you don't need to buy it for the course, but it is a good book. So if you're going to use RStudio and you're going to go on to use it in the future, then I would thoroughly recommend you look at getting it. But anyway, Hadley is the person who's created the tidyverse, which is a whole set of packages within R in order to visualize data, manipulate data, analyze data, and he's actually the chief scientist at RStudio. So this is someone that you want to pay attention to. Anyway, the point I'm trying to emphasize here is that Hadley's approach that he portrays in this book is that with RStudio, you're basically able to import some data. You can use some of his packages that he's created, whether that's tidy or whether that's ggplot2 to visualize. But basically, you're able to manipulate the data, transform it, visualize it, build a model, and then go through that process until you're actually able to draw some conclusions, and then you're able to communicate it. All right. So I will get into more advanced ways for how we kind of hypothesize about the world, and then kind of either carry out descriptive statistics or inferential statistics. And I'll get to that later. But just for this week, this is nice and easy. It's not too complicated. And hopefully you can start to kind of get your head around the fact that this is an iterative process. So we're going to have a question about the world that we want to understand. We're going to grab some data about it. We're going to analyze it, maybe build a model or two, draw some conclusions, and then we're potentially able to communicate that to other people to hopefully make the world a better place. So John Tukey is a famous mathematician, and he made this statement that I really like, which is that basically the simple graph has brought more information to the data analyst's mind than any other device. And I think that's probably true. I always remember a really advanced researcher that I worked with when I was just starting out on my PhD, and he would always say, you know, when you're starting on a new data problem, the first thing that you need to do is you just need to plot the correlations and understand the descriptive stats. And, you know, he was very advanced quantitatively, and he would just be like, the first thing you need to do is all these basic things, which is like plot all the data in a set of different plots so you can understand the key principles, start to generalize and understand how patterns are taking place in the data. And it's very visual, you know, this isn't about numbers at this point, it's actually about trying to see the relationships. Okay, so anyway, my point is that visualization is great. I would say that I was definitely I struggled when I was learning this, when I was at your point. And I think that that's because I was a bit overwhelmed. I was overwhelmed because there's all these different types of visualization techniques. I don't really understand what most of them do. And I know that I need to kind of use some in my dissertation in order to get my degree. And that's, you know, that's pretty daunting. So what I decided to do was to introduce you to this kind of decision chart. So this is a way to help you understand which potential plots you may want to use in order to visualize the data that you have. So the question is, well, what would you like to show? Is it a comparison? Is it a distribution? Is it a composition? Is it a relationship? And then once you go into each one of those categories in the flowchart, you're able to understand which potential chart you should use, depending on the number of data points that you've got, whether it's a share of a total, whether it's a relative difference or whatever. So I just want to go through each one of these and talk a little about the point of some of these graphs. So distributions, this is something that we will come back to very regularly. So histograms are something that we're going to cover here. So you can have a column histogram, which we're going to touch on in a short time. A line histogram, which is just a column histogram, but someone's actually just drawn a line through the very top points of the blocks. That's important to remember. A scatter chart. So this is so important for you guys to get and understand. So if you have two variables that both quantitative, for example, then you can plot them against each other to understand the relationship, whether they're positively correlated or negatively correlated. And if you're feeling really brave, you could do a 3D area chart. Now, I think that this is really quite a polarizing topic in the data visualization world. I think all the data geeks probably love 3D charts, but I definitely know of people who say you should never put three axes on a chart because it's just too much information to people to try and take in. So that's kind of a that's maybe you can do that if you're feeling brave. Okay, so let's move on and give you a flavor of that type of data. So essentially, to generate a histogram, what I have here is a list of ages. So this, if I was writing in Python, this is basically how you would create a list. And so you've got people here, someone who's 21, 25, 34, 34, 37, so on and so forth. Okay, so this is all the underlying data. If you don't want to think of it in terms of a Python list, let's just think that this is a spreadsheet and it's got a set of rows and just got a bunch of data, okay? The point of the histogram is that we're able to actually tally up and add up all of the different ages depending on some preset segments. So maybe we want all the people between 20 and 30, the people between 30 and 40, and we want them all in their own groups. So let's go up in 10-year, decade increments essentially, and let's look at the frequency of the observations, and let's actually plot them using a vertical bar chart. So essentially what we're doing here is we are aggregating that data that I've just shown you. So these are the raw data points. Now what we're doing is we're actually looking at the frequency. So for the ages 20 to 30, within that segment, sometimes these are called buckets, we actually have 2 people who fit within that bucket, within our data set, okay? And then you can look at all the different age categories. So we can see here the ages of 50 to 60, between those ages we have 5 people within our data set. So that's actually the largest, the most frequent age bucket that we have, the age segment. Okay, and that's why it's got the largest bar. So hopefully you're able to understand that particular pattern. This is how we look at a distribution for a single variable. Okay, so now let's think more about multiple variables. So actually I did this project quite recently. Actually, I've done it in the last year. And what I did was I did a survey, a wireless survey, where I would passively detect Wi-Fi hotspots in central London for Facebook research. So some of the work that I do with Facebook focuses on internet connectivity, trying to connect more people to a faster internet. That's just so important. You know, everything is online these days. A lot of the kind of methods that we've developed help to understand how to design the networks, how to understand how many assets have been deployed. And the thing about Wi-Fi hotspots is that you go out and you buy your cable subscription or whatever, and you fit your Wi-Fi device. There is no single database of those data points. So essentially, there is no one who understands where all the internet assets are. It just doesn't exist, because it's something which you and I go and set up ourselves. There's no overarching administrator or coordinator. It's an emergent network. But this actually means that we need ways to try and detect and understand how many assets are actually deployed. So the point of me going around with a cell phone and basically picking up all the Wi-Fi hotspots that my phone pings onto when I'm driving around or cycling around or walking around, is that we can start to understand how many how many Wi-Fi hotspots are actually present in a particular area. Okay, so you can look at the paper which I wrote for this particular piece of work. The link's at the bottom just here. But essentially what I did was I was able to correlate the number of Wi-Fi access points to the building count, and the building count data came from national statistical data. You can basically make an estimate of the buildings based on the satellite imagery. Okay, so you can do image recognition on the building shape, and then you can do that repeatedly until you have an estimate of the number of buildings in an area. So the point here is that I have a histogram and I have 2 variables. So I have the building count per decile on the x-axis, and then I have the number of Wi-Fi access points on the y-axis. And that gives us an ability to actually plot these 2 different variables on a single plot. Okay, so this is just giving you a flavor for how you might do that type of histogram using 2 different variables. Okay, so that gave you an example of distributions. Now let's think a little bit about composition. So this could be a static composition, or it could be a change over time. So a piece of work that I did a few years ago was actually for the Dutch government. So I developed analytics which informed their 5G rollout. So in about 2016, I started building models for 5G. There's a lot of hype around 5G right now, and as a consequence, there's a lot of government policy that needs to be introduced in order to expedite rollout of it. I mean, that's been particularly driven home by the fact that the COVID pandemic has required everyone to be remote working as well. So it's kind of changed the landscape a little bit. But anyway, the point is that in this graph just here, what I've actually got categories on the x-axis, costs on the y-axis, but then you can actually see that the bars are made up of compositions, and those are the different cost types. So these are aspects of the investment required to deliver 5G to people living in urban, suburban, or rural areas based on the population density. It demonstrates the cost, it demonstrates the composition of the cost that needs to be spent on different parts of the engineered system. Okay, so you can look at the paper if you're interested in this particular piece of work applied to the Netherlands, or you can look at this graphic, for example. So this is just the previous graphic. I just didn't want to bombard you the first time round with a big panel plot. But I mean, this is how fun the visualization gets, okay? So after a while, it gets kind of addictive, and it's a bit of an art form because you're able to visualize so many different things on a single plot. And if you can do that intelligently, it's an incredibly powerful tool. So here I have different strategies on the y-axis: spectrum integration, small cell deployment, or hybrid network deployment. So just imagine that as 5G strategies. And then on the actual panel x-axis going across, I have the different amount of capacity. So do we want to deliver users like yourself 30 megabits per second, 30 meg, or 100 meg, or 300 meg? So, you're walking down the street, you want to stream a TikTok video, or you want to stream an Instagram video. Basically, it matters how much capacity you have, because that's going to dictate how quickly you're going to be able to stream that content, okay? So this just gives you a bit of a flavor of what you can do with those compositions, and stacked bar charts are always a really nice way to go. So that's composition. Now let's move on to relationships. Within a scatter plot, so I know that I can't remember whether we touched on scatter plots already. I think I just talked about them in a high level, but you can actually plot more than two dimensions on a scatter plot. So obviously here we have the x-axis and the y-axis. So this is actually the petal length on a set of plants and the petal width on a set of plants. And this is a very famous data set. It's very old, but it's one of those classic R data sets that people go to. It describes a set of flowers, I think. Anyway, the point is that you're able to show the relationship of the sizes of those data points that you have on this graph, along with a third dimension, which essentially is the species type. Okay, so you see on the right-hand side here, we've got the species type, and then this gives you an extra way to start to introduce more dimensions into your plotting capabilities. So I think we also had bubble charts within this particular category. So I've shown you scatter charts already. Now let's think about bubble charts. I did actually use a bubble in this piece of analysis that I did it was for the UK Met Office. So this is the equivalent of the NOAA in the US. So basically, these are the people who do a lot of the Earth observation, particularly weather forecasting, for example. But in this case, it was actually space weather forecasting. So I don't want to get too much into it, but there's phenomena that happens on the sun, and that can affect our technology on Earth. And as a consequence, it can create things called geomagnetic storms, which are electrical storms, essentially, which happen in the Earth, and they affect our technology. The point is that here I used a bubble chart to actually visually show the amount of current that was produced and flowing over transformers in the high voltage electrical grid using bubbles. Okay, so if you look on the right hand side, and then you look on the plot A and C, you can see that the bubble size directly relates to a variety of different factors. So actually here, this is if you look at the main paper, it has the diagrams I mentioned before, but here we have the population per node, the transformer count per node, and the voltage per node. So essentially you're able to locate something in space and then show the size of a particular metric using, in this case, a bubble. But actually, I think many of you who are doing the GIS, minor or major, or some sort of GIS course will be familiar with these types of charts. I don't think it will be too complicated for you to kind of pick up and understand the use of these particular visualization formats. Okay, and I've provided some details for you here. Definitely check out Hans Rosling's 200 Countries in 200 Years. It's 4 minutes. Sadly, Hans is no longer with us anymore. he passed away, I think, a couple of years ago. But this is really one of those beautiful ways to visualize data, and he used moving bubble plots to look at, I think, is the relationship between it's the development of countries over time, essentially. So you're able to look at I think it's life expectancy and wealth. I'm trying to remember off the top of my head now, but this is one of those beautiful kind of seminal statistical examples of how you visualize quite a lot of data and actually portray it to a really wide audience. So this is incredibly famous, and you should definitely take a look at his work, because he not only presents it really nicely, but it's also explained very well. And I think in this particular video, he'll give you a nice explanation as to kind of what's happening with those trends as you look over the last 1 or 2 centuries. Okay, so that was relationships. Now let's focus on comparisons. So I did a piece of work a couple of years ago which focused on analysing space weather risks to the US electrical grid. So it's actually for the insurance industry, so AIG, American International Group, which is one of the largest insurers in the world. Their main head office is in New York, in Manhattan. And because they're an insurer, they take money from companies or households in return for an event that might happen in the future. So what they do is they invest that money, and at some point they might have to pay some of it out. But as a consequence, risk analytics are really important to them. So they're interested in any type of risk that could destroy their balance sheet. So hurricanes, earthquakes, in this case space weather. Whereas those two former natural hazards, hurricanes and earthquakes, have had loads of research done on them. There really hasn't been that much work done on space weather, and that's why we were getting funding to work on this particular area. Okay, so I just wanted to demonstrate using the data from this particular paper, which you can follow just here on the bottom left of your screen, in order to show the actual comparison between different factors. So when I did this work on the US and I looked at these different scenario events, so imagine we had blackouts which covered different states running across the US here. There would be a direct customer disruption, so that's like the number of households or businesses disconnected from the grid. That would lead to a direct loss, economic loss, so lost gross value add, because you can't do the economic transactions that you normally do on a daily basis. You can't sell products to your customers. You can't buy products from other companies. So anyway, the point is that I used a composition in order to demonstrate whether the quantity of lost gross value added here, so it's a measure of economic activity, was direct, indirect downstream, or indirect upstream. Okay, so if it's direct, then I don't have power, so I can't go and buy something that I want. If it's indirect downstream, that means that I can't sell my product to someone who wants to buy it further down a supply chain from me. And if it's indirect upstream, it means that I can't purchase my product from someone who's higher up in the supply chain from me. Okay, and using a quantitative modeling technique, I was able to actually quantify how these effects take place given particular blackout zones across different states. Okay, so it's very high level, but it just provided us with some understanding as to how the different spatial distribution of economic activities fed through to economic losses based on supply chain disruption if there was a space weather event that managed to knock out the electricity grid. Okay, great. So I think this is now just finishing up, basically, so focusing on the temporal aspects of displaying data. So this is pretty common. There's not too much to say here except that this is a time it's a time plot, essentially, a time series chart that I produced for internet penetration. So it's the number of people who have actually adopted internet services. It's the rate per 100 people for the top 6 economies. So that's essentially US, China, Japan. I'm trying to put them in economic size here. Germany, United Kingdom, and then France. So that was the order in economic size at the time of me creating this. I think that India might well be taking over France at some point. I think India probably will become, this order will end up changing quite rapidly in the next 10 years. It's already a little bit out of date now. But anyway, going back to the plot, what you can see here is for each year, you can see who's been adopting the internet. So the US basically had much higher adoption of internet services from about 1992, 1993. The number of people adopting really shot up. So that went all the way up to the millennium, so 2000, where the US was way out ahead. And then you had a bunch of the European countries essentially adopting relatively quickly in the middle of the pack. And then I think you have France and China as the outliers there who are adopting slower. But yeah, I think they all end up going to the same, about the same place in the end, except for China, which probably won't be too far off catching up now if we were to extrapolate forward to today's data. Okay, so this gives you an understanding of how you can plot data with some sort of measure against a time series. So you may have the number of years, usually always on the x-axis, and then you have your data value on the y-axis. So that's about it. I think I've covered all of those different areas now. So when you have a dissertation topic or you have a paper that you need to write and need to visualize some data, do remember Ed told me that there was a way for me to get the right plot based on those different factors within my data. Okay, so you can go to this and hopefully it'll give you a bit more guidance as to which one you need to pick. We are going to be using RStudio, so I thought I would just point you to Hadley Wickham's ggplot2 data visualization cheat sheet. So this looks incredibly complicated, it looks really horrible, but I think the key point is that this is an incredibly powerful package, and this is a cheat sheet that allows you to do basically everything. So once you have a little bit of knowledge, you can do all of the graphs that I just showed you before. And this seems quite abstract and high level. Don't worry, we will get to it in the future. I just want to point to you that this is the type of simplified diagram that will really help you be able to deliver on the graph that you've chosen once you've been able to work out which one you need to pick. Okay. And why? Why are we even doing this? Why are you even signed up to my class and to this quant methods class? You know, maybe you have a bit of maths anxiety, which is totally understandable. Maybe you don't really, you're a bit apprehensive about the work that we're going to be doing. Well, you know, ultimately, the more quantitative you are, the fact of life is that the higher your salary will end up being once you leave college. Okay, so here I've just put a graph which demonstrates the distribution of salaries, including the median starting salary for people who have taken different degrees, essentially. So at the very bottom, you've got quite a lot of areas that aren't that quantitative. So education, religion, design, music, nutrition. And then towards the top of the graph, you actually have a lot of highly quantitative areas, so engineering, economics, physics, computer science, math. Great. So my point is that it's not all about money. I totally understand that, and you know, I definitely feel that. But what I would say is, with just a small amount of statistical insight, you know, say you manage to grasp this course and you manage to use R in the way that I'm going to show you, really you become so much more employable. You can put on your CV, on your resume, that you use R, that you're, you know, a basic to intermediate user, that you can statistically analyze data, that you can visualize data. You're not just more employable as well, and you don't just make more money potentially, but you're also less likely to be unemployed, because these are the types of skills that are really in high demand. You basically become a desirable piece of property for any employer, and therefore harder to dispense with. Okay, so that's about it from me. This has been the first lecture, the first proper lecture for the GGS300 Quantitative Methods course. It's been great to see you here today. There will be a lab video that I will follow up in, essentially where we're going to look at how we actually install RStudio, and we're going to look at doing some basic commands. So I'm essentially going to introduce you to the command line, which will be really fun. So that's all very exciting, and I'll look forward to seeing you then. And let me know if you've got any questions or queries. And I hope you're all doing well. So thanks for tuning in. Goodbye.